Wait, PyTorch's AutoGrad, JAX's grad, TensorFlow's gradient tape. Are they all secretly doing the same thing?
They rest on one quiet idea. We can compute exact derivatives by mechanically applying the chain rule. And the whole interface fits in a single function, called grad. It takes a function, and it returns that function's gradient function. Take f of x equal to the sum of x squared. Then grad of f gives us df, and df of x is 2x. Feed in the column vector 1, 2, 3, and it hands back 2, 4, 6. No symbolic algebra by hand, no derivative rules typed out. Just call grad and call the result. And because grad returns a callable, you can feed its output straight back in. Grad of f is the second derivative. There are no classes to instantiate, and no global state to manage anywhere. Just functions transforming functions. The grad function itself reveals the whole algorithm in 5 short steps. Make a fresh graph, create an input variable from the data, run the forward pass, which is simply calling f of x and getting a value back, run the backward pass, and finally, read off the gradient. 5 lines, and every one of them is plain. Here is the trick of the forward pass. When f of x runs, every operation quietly creates a node. In the graph,
Hold on, doesn't that mean every operation has to carry its own calculus around?
exactly that. Each node stores 3 things: the value it just computed, references to its parent nodes, and a backward function. That implements that operation's Jacobian. The value flows forward, the backward function waits for later. For f of x equal to the sum of x squared, the graph is a short chain. The input x flows into a squaring node, which flows into a sum node, which produces the scalar loss. Building the graph is nothing more than running the function. The structure records itself as the computation happens. Now we run the very same graph in reverse. We start at the output and seed its gradient to 1. After all, the derivative of the loss with respect to itself is simply 1. That single seed is what we propagate backward through everything we built.
But how do you know which order to walk the nodes in?
From there, we walk the nodes in reverse topological order. Because we built the graph with children placed after their parents, iterating the list backward automatically respects every dependency. Each node's backward function takes the gradient arriving from above and passes it down to its parents, using the chain rule. Through the sum node, the gradient becomes a matrix of 1s. Through the squaring node, it becomes 2x. Out the bottom, the gradient at x is 2x, the vector 2, 4, 6. Exactly what calculus would have told us, only here it was computed mechanically, by following arrows in reverse.
So adding a new operation doesn't touch the traversal code at all.
Not a line of it. Step back and the pattern is striking. Every differentiable operation is the same kind of object: a forward value, a list of parents, and a backward function that is the operation's local Jacobian. The backward traversal itself never changes. To teach the system a brand new operation, you supply exactly one thing, its Jacobian. Let us look at 3 from matrix calculus. First, matrix multiplication. C equals A times B, the matrix product. Given the gradient flowing back into C, the chain rule hands us 2 results. The gradient with respect to A is the gradient of C times B transpose, and the gradient with respect to B is a transpose times the gradient of C itself. Second, the determinant. D equals the determinant of A itself. This is a classic matrix calculus result. The gradient is the determinant of A times the transpose of the inverse of A itself. One scalar out, a whole matrix of derivatives back.
3 totally different formulas, and the algorithm around them stayed the same.
Every time. Third, the matrix inverse. B equals A inverse. Differentiate the identity A times A inverse equals the identity matrix, and the adjoint falls right out. The gradient with respect to A is minus A inverse transpose times the gradient with respect to B times A inverse transpose. 3 very different formulas, and yet the algorithm around them never moved. We only swapped the Jacobian. One more rule completes the picture. What happens when a single variable is used more than once in a computation? Its gradients accumulate. They add together. This is the only place Fanon matters, and it is handled in one place.
Wait, if y is x plus x, isn't the derivative just 1?
That is the trap. Take y equal to x plus x. The derivative of y with respect to x is 2. Not 1. Each separate use of x sends back its own gradient of 1, and the two contributions sum. Forget that, and you would silently have your derivative. Now stack the idea. Let y be x plus x, then return y plus y, doubling it once more. There are 4 paths back to x, and the gradient is 4. The accumulate function does precisely this. If a node has no gradient yet, it stores the incoming one. Otherwise, it adds. Summation is the whole secret of correctly handling a variable that reappears.
A fair question hangs over all of this. How do we know any of these Jacobians are actually correct?
We check them against finite differences, which are the computational echo of the very limit that defines a derivative. We use the central difference. F prime of x is approximately f of x plus h, minus f of x minus h, all divided by 2h, a small step size. This symmetric form has error of order h squared, noticeably better than the one-sided difference, which only gets you order h itself. Finite differences are slow and approximate. They need on the order of n function evaluations for n parameters, and they carry rounding error. Automatic differentiation, by contrast, is exact and needs a single backward pass. But finite differences do not lie. And that is exactly why they make the perfect ground truth to test our gradients against. Here is where it all pays off: gradient descent. This is logistic regression with a binary cross-entropy loss. Wrap the loss in grad, then loop. Compute the gradient and nudge the weights a small step downhill. Change the loss function, and grad adapts on its own. Nothing else in the training loop has to move. So automatic differentiation is not magic. It rests on 3 plain ideas: graph construction during the forward pass, backward traversal in reverse topological order, and gradient accumulation wherever a variable repeats. That is the entire machine.
So when PyTorch calls dot backward, it isn't doing anything we haven't already built.
Nothing more. It is doing exactly what we just built: walking the graph, calling backward functions, summing gradients. Reverse mode automatic differentiation is the chain rule, applied systematically. Once you have seen the machine, it is just the chain rule.